Good evening, everybody. Here with another video for you all. This one's a little different. It's not focusing on Anki today. This one is just statistics lecture, the correlation and predictive techniques. So I thought I'd change up a little bit of the content I provide for you. And hopefully you find this helpful, because I know some people were having some trouble with the statistics lecture, and I thought I'd try to summarize it really well for you all. So just to bring you up to speed on what this is going to go over, I tried to take this lecture and all of its details and try to put it into a kind of a digested format, one pager per se, to digest pretty easily. So I focused on the learning objectives, and there was a lot of information in this, and the learning objectives did not directly mention some things, so I chose to left those out. But throughout this, I will reference going back to the lecture slides for you to learn as well. So here is the picture of the whiteboard that I have behind me. I just thought that this would be a little easier to see than the whiteboard, and this will be attached to the video. So if you want to follow along, take notes, you can grab this picture from the video and edit it as you see fit. But I'm just going to jump right in. So we're going over correlation in statistics. So to start that, it simply is just you're seeing if there's a correlation with data, specifically an X variable with a Y variable. Like, is this somehow correlating with this result? And the way you plot that initially is a scatter plot. So you just put all of these little dots on a graph, and then you see if there's a line of best fit that applies to that. And then putting that line through allows you to get a correlation if there is one. So here's some examples. There you have a positive here, where if you use Excel for some graphing function, or if you did all the calculations yourself, you see that there's a positive slope if you were to put a line through that, a negative here, and this one is just completely random and there's no slope, there's no correlation, so you'd have a slope of 0. And so that is correlation statistics, simply put. And then we went into two kinds of tests before we jumped into regression analysis. Those two tests are the Pearson test and the Spearman test. So the Pearson test uses a correlation factor of R, and this test measures the relationship between two interval or ratio level variables. So that's going back to, I believe, ISOM, when we learned about types of data. So an example of this is like ratios or intervals. So how much salt does a patient intake in a daily or weekly time frame, and what is their blood pressure? So like ratio of how much salt do they have on a day on average, and then what is their blood pressure typically. So like a ratio in the blood pressure is ratio level. And so you can look at the calculations, but basically what you get from this is R, a value, and that'll range from -1 to +1, with +1, +1 being a positive correlation, -1 being a negative. And if you have 0 in the middle, and then you spread it out, you'll get, you won't get +1, -1, or 0 every time. You'll get a decimal within that. And you can measure the strength of that correlation then by depending on the decimal. So there's a slide in the lecture that goes over the strength of correlation. It is slide 8, where it shows there's a low correlation, a moderate, a high or strong, and a very high. And then you just flip the sign on positive or negative, depending on if it's positive or negative correlation. And I just want to mention this as well, that if you square R squared, that measures the proportion of variance in one variable in respect to the other. So that's just I'm just going to leave it at that. Just know that R squared measures the variance, kind of like going back to what I want to say, standard deviation. Don't quote me on that. But that will give you variance in respect to the other. And then overall, Pearson test measures parametric data. And we'll get back to that in a minute. But parametric data for this one, for the Pearson test. And then the Spearman test, I forgot a T there. Spearman test has a correlation factor, or what it measures is a row factor. And this compares ordinal scale data. So generally stuff that has rankings. And so an example is like birth order and class position in school. So birth order is nominal. And then you have your class position in school, which is giving a ranking. And this does measure or test nominal data. So this is part of nominal. And again, it follows a range of 0 or -1 to +1 with the same strength rankings as the Pearson test up here. And this measures non-parametric data. And so the slides were kind of confusing on parametric versus non-parametric. And then there's like a in between of those two when he was going over, let me find it here, the exact words. The semi-parametric methods, which is going into the Cox regression. But to put it simply, I found this figure and I found that it summarized it well. So parametric test used for ratio interval data, which matches up with our Pearson test pretty well. And then you have the non-parametric test for ordinal or nominal data, which follows the Spearman data test, like the definition. So you can read this further if you would like. You can pause it here, try to process this because statistics is challenging. It took me a minute to understand this so I could make this video. But pause it here for that. Otherwise, we'll keep going and we'll jump right into regression analysis. And so the first one is a simple linear regression. This is going right into kind of some old algebraic math that we did quite some time ago. So that's your y equals mx plus b, or I'm going to stick with his nomenclature of y equals bx plus a, with x being your x-intercept, y being your y-intercept, or x being your x value, y being your y value. Sorry, ignore the intercepts part. X being your x value, y being your y value. B is your slope, so that's your change in y or change in x. And then A is your y-intercept. And just to give a brief summary of what linear regressions is, they're a line of best fit when put on a scatter plot, but otherwise it's just a linear line. And then that sign of, I kept M there. That should be a B. Sign of B dictates whether it's a positive or a negative correlation in regards to a regression analysis. And then there's the learning objective that jumps into defining causality with versus correlation. And that can be confusing. And it basically boils down to that with causation, if you are looking for causation, you are saying that X gives you Y, and that's your statement. But with statistics, we can't say that. Or with this, for our purposes, we're not saying that. We're not saying X gives you Y. We are looking at if X correlates with Y, then that is rejecting your null hypothesis here, which your null hypothesis is that B equals 0, your slope B equals 0, going back to this scatter plot here where there is no correlation. That is if there's no correlation, that's your null. So if you accept your null, done, no correlation, no significance. If you do reject it, if you do find a correlation, if in any way your slope is not 0, you're rejecting the null and you should investigate that. That's when you should look into what that correlation may be. And that does not necessarily imply causation. That doesn't mean X causes Y. That just means that they correlate, they kind of follow a pattern. And then the last bit of linear regression analysis before we move on to the more complex tests is that residual error, any error that's left from your data, so kind of like the standard error that we calculated previously, the residual error is you add that into your equation. It is the difference between your expected, like your predicted and your actual. And so it just gives you this equation here that takes into account a residual error when you do plot that final data on your final graph that you would present. So you just have a predicted outcome versus a not, or predicted minus your actual gives you your error. And I believe, let me check that actually, that I have those equations right, or those variables right. Pretty sure the y what the caret is. Yeah, oh, sorry. Predicted or observed minus predicted. Sorry, observed minus predicted gives you your residual error. Observed minus predicted gives you E. Okay, moving on. Multiple linear regression. This is pretty much the same thing as simple linear regression, except you're just adding in another independent variable. So that goes into the learning objective of what is like define a dependent and independent variable. That's just going way back. That dependent variable is what you're measuring. Independent variable are factors that you are monitoring, holding constant or changing, like you change and then you hold constant, that affect your dependent variable, your outcome. So y is our dependent variable. X's, in case the multiple x's are your independent variables. So we are adding another independent variable or more here. And so this is going to be your equation. You can keep adding it like a B3 and an X3 and so on and so on. And then to connect it back to, how are we going to interpret that data? You're going to look at like the value of B1, which would be a kind of like a slope, different. The graph is going to look different. It's not going to be linear, but B1 is going to give you your change in Y over your change in X1 when all the other X's are held constant. So that's kind of how you would interpret that piece of data. I'm trying not to dive into the weeds too much here. That is a multiple linear regression. So when you have multiple independent variables affecting your outcome, or correlating with your outcome, if that makes more sense, if that's better terminology for statistics. And again, if you reject your null hypothesis, you should investigate that. That is looking at if you have a strong correlation or weak correlation or a moderate correlation. And again, that does not necessarily give causality, it shows correlation. And then we will go into some harder stuff. I think the logistics regression or the odds ratio kind of connected that the logistics regression is this test and that you can describe it better with odds ratio. So if you want to look at more of the odds ratio, I recommend going and looking at that. It's kind of saying like, I don't know how to put it. I recommend go reading this because that one kind of makes sense with going over the examples. It's like taking the simple odds of, I don't know, if you're in this, like if you're above the age of 50, his examples, if you're above the age of 55, what are your chances of developing like CHF versus not? And then comparing that to if you're under the age of 55, what are your chances of developing CHF versus not? And so it's just developing up an odd, you can find the odds of getting CHF in each age group, and then you divide those two, get a ratio. That's odds ratio. That's a way of describing logistic regression, which predicts the success or of a probability of an individual success. Let me start over. Predicts the success probability of an individual falling into one category or another. So it's the success probability or just the probability if they're going to my right hand or my left hand. Like it's just going in one of two categories, or if there's multiple categories, but just the probability of going in a category. And so Y, your outcome would be the percent success of going into one category or another. And that means that your dependent variable, your Y, your outcome needs to be a category. So whether that's binary or multinomial data, like for example, I'm trying to connect it maybe to us. If you are a coffee drinker while studying or a non-coffee drinker studying, I'm definitely a coffee drinker in medical school and I drink a lot of coffee. So I would fall in the coffee drinker category. And there's a bunch of data and a bunch of equations with this. So I left out all the equations. But something that might be of note is that logistic regression and odds ratio is not straight. It's not a straight curve, not a straight graph. So because your percent of success can vary depending on your X and Y. It's not a linear correlation. What if you take the logarithm of that? It goes and turns into a linear regression of that. So the log of that equation that you can look at in the slides, it's super big and kind of daunting. Turns into a linear regression if you take the log of it. And then we'll go into the Cox regression. And I just tried to summarize what the Cox regression is in words and take away the math that scares us. The Cox regression measures the time needed for a specific event to happen based upon multiple factors related to survival. Survival, we'll go into in a minute, but generally compares the baseline event of a or hazard. So compares, say, me, let's see if I can connect back. So the baseline event of me tripping in the hallway while walking at school to the events of that happening, of me tripping in the school with multiple other like factors involved. So baseline event of me walking and tripping at school, that's say like 10% that's going to happen. But then say I injure my hip and I'm wearing different shoes that day, and say I'm feeling nauseous. So adding 3 other variables in there. That is the event. That is then the probability of the event happening with all those other factors. And that'd probably be like 30%. And so that's what the Cox regression is looking at. It's the time of an event happening, like how soon it's going to happen, or the probability of that happening within a given time. If you, from the baseline, when there's no other factors, and then if you add other factors in, like how is it going to change that time for that event to happen? And then that goes into survival analysis, because Cox regression is a part of survival analysis. And survival analysis is the time to the event. We're looking at time until something happens. So that's whether or not someone suffers the event or the follow-up time from the initial event until the next. So in my case, tripping while walking at school is whether or not I do that. But follow-up time from the initial event until the next event, that could be like heart attacks for our patients, or say panic attacks for people that have anxiety, or like car wrecks. Like what's the time period between having your first car wreck and your second car wreck, with additive factors in between that could change that time. And so just kind of to put it in terms of this, like some math equations, your survival time is the time interval between your T naught, your T0. So whether that's time of never having it or your initial time, and then the time of the event happening. And then they term that T1 failure. So kind of like you failed to pass that time period indefinitely without having that event. So that is survival analysis. And then in these studies, looking at to see if someone has that event, there's times when you don't get to collect data on that patient or that dependent variable or sample. And then what you would do is censor it. So that's the survival time is not known for a patient or one of your samples. And that is due to 3 factors. So whether or not they did not experience the event while during the period the study was active, and then the study ended, and then you don't know what if they happened to them after that because the study's over, or if they chose not to follow up with the study, like they just didn't tell you what happened, or if they withdrew from the study before it ended. And then lastly, I just wanted to show you a graph of what survival analysis is. So the probability of survival is the y-axis, so the chance of success, or you could change this and like percent probability of having an event compared to time. So you could say like this is the probability of survival of me as I prep for finals week. But it should be the other way, right? Should be the way. I should be optimistic. And that should be, or you can put that in an equation as like the probability of survival or success is given by, I can't remember what ST means off the top of my head. It's in the slide. That is just your, that is your ratio of like how many patients or samples are surviving given that time period, given time. And so to put it as like a ratio is like how many or have survived, like how many patients have survived over total patients. Okay, let me retry that. P is your total amount of patients that have survived, your number of patients that have survived over your total number of patients that you started with at a given time. That is P. So P would be like picking a point out here. And that P would be your probability of survival. And you would get that by measuring your survived over your total you started with at a given time. Okay. And I hope this was helpful. I just want to make the disclaimer that, I don't have a degree in statistics. And I just followed the learning objectives, trying to learn from the slides. So I hope this is helpful, but, I probably missed some things or did not explain some things fully correctly compared to the lecture. So use this at your discretion, and please let me know if anything is incorrect or I said it wrong, and leave that in the comments. So if anyone watching after, you can learn from what I just said poorly. But best of luck studying, everyone. I hope you find this helpful. And I will see you throughout the week. Cheers.